These are physicists who broke a rule that was supposed to be unbreakable, and the way they did it forces us to rethink what the word cold even means. This video covers absolute zero, the temperature scientists spent 2 centuries proving nothing could ever cross, and the handful of laboratory experiments that found a strange loophole in that rule without actually violating it. Before we're done, we'll walk through superconductors that carry electricity forever without losing a single watt, helium that climbs up and over the walls of its own container as if gravity had simply stopped applying to it, a nesting pair of pigeons that got blamed for the leftover heat of the Big Bang, a dead star that turns out to be quietly superfluid at its core, a cubic meter of copper buried under an Italian mountain that may be the coldest object in the entire universe, and a Bose-Einstein condensate cooled to 38 trillionths of a degree above nothing at all. Stick around, because the answer to the question in the title is both simpler and stranger than you'd expect. And if you're the kind of person who likes taking a simple-sounding question apart until it stops being simple, go ahead and hit subscribe before we get into it, because that's exactly what the next while is going to be. Let's start with the number everybody thinks they already understand. Absolute zero sits at 0 Kelvin, which works out to minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. Most people who've heard the phrase picture it as the coldest possible temperature, full stop, the floor beneath which nothing can exist. And for well over a century, physicists treated it exactly that way too. But here's the thing that makes this whole topic worth the time. A small number of laboratory experiments, going back to 1951 and continuing all the way through 2013, have produced systems that physicists genuinely describe using the language of negative temperature. Numbers that on paper sit below zero on the Kelvin scale. Numbers that would seem to break the one rule everybody agreed couldn't be broken. So the question this video is built around isn't a trick question, and it isn't clickbait dressed up as physics. It's a real question that real physicists have spent decades arguing about, sometimes in the pages of Nature Physics, sometimes in dueling papers on archive that read, if you squint, like a polite academic shouting match stretched out over several years. Can anything actually get colder than absolute zero? Or is something else going on entirely? Something that only looks like it's breaking the rule, while actually obeying an even stranger one hidden underneath? To answer that properly, we need to slow down and understand what temperature actually is in the first place. Because most of us walk around with an intuition about temperature that's built for weather forecasts and kitchen thermometers, not for the kind of physics happening inside a vacuum chamber, cooled to a few billionths of a degree above nothing. What temperature actually measures? Start with the everyday version, the one you already carry around without thinking about it. When you touch something cold, what you're actually feeling is heat leaving your hand and flowing into the object. When you touch something hot, heat is flowing the other direction, into you. That flow only ever runs one way on its own, always from hot toward cold, never the reverse, and that one-way rule is baked directly into the second law of thermodynamics. It's the reason a cup of coffee left on a desk cools down to room temperature and never once, in the history of coffee, spontaneously heats itself back up. But underneath that everyday experience sits a more precise definition, and it's the one physicists actually reach for when they talk seriously about temperature scales. Temperature, in the language of statistical mechanics, describes how chaotically the particles inside a substance are moving. A hot gas is a crowd of particles zipping around at high speed in every direction at once. A cold gas is that same crowd, only sluggish, barely shuffling in place. Follow that logic all the way down to its natural conclusion, and you arrive at a floor, a temperature at which particles have given up essentially all of their kinetic energy and simply stopped moving. That's absolute zero, and for most of the history of physics, nothing was allowed to go below it, for a reason that sounds almost too obvious to state out loud. You can't have less motion than no motion at all. That idea, a genuine flaw built into the structure of the universe, didn't appear out of nowhere, and it wasn't obvious for most of the history of science. Ancient and medieval natural philosophers had rough, workable concepts of hot and cold, but nothing resembling a true absolute scale, nothing with a bottom. What changed things was a 19th century physicist working out of Glasgow, and the paper he wrote in 1848 quietly reshaped how every scientist on the planet would talk about temperature from that point forward. It's worth spending a few minutes on him, because his story sets up almost everything that follows in this video. Lord Kelvin and the invention of absolute zero. His name was William Thomson, and he was born in Belfast, Ireland, on June 26, 1824, the fourth of 7 children born to a mathematics professor. His mother died when he was only 6 years old, and in 1833, when Thomson was 9, his father was appointed to a professorship at the University of Glasgow, so the family packed up and relocated to Scotland. Thomson turned out to be one of those rare people whose talent shows up embarrassingly early and never lets up. By the age of 22, he had already become Professor of Natural Philosophy at the University of Glasgow, a chair he would go on to hold for the next 53 years of his life, an almost unthinkable span of time to occupy a single academic post. Over the course of his career, he published more than 650 papers, spanning electromagnetism, thermodynamics, hydrodynamics, and geophysics, and he held patents on roughly 70 separate inventions, which tells you this wasn't a man who confined himself to one narrow specialty and stayed there. What concerns us here, though, is a paper he wrote in 1848, titled, in the characteristically wordy academic style of the period, On an Absolute Thermometric Scale, founded on Carnot's theory of the motive power of heat, and calculated from Regnier's observations. Thomson had encountered the theoretical groundwork for this idea more than a decade earlier, back in 1837, through a translation of a paper by Clapeyron that summarized the work of French physicist Sadi Carnot on the theory of heat engines. Carnot had shown, years before, that there were fundamental limits to how efficiently heat could ever be converted into mechanical work, and buried inside that engineering-flavored analysis was a mathematical structure that didn't depend on the quirks of any particular substance, whether that substance was mercury, water, or ordinary air. Thomson realized that structure could be repurposed into something far more ambitious than an engineering limit. It could become a temperature scale that wasn't tied to any specific material at all, unlike the mercury thermometer or the alcohol thermometer that everyone was using in daily life at the time. He combined Carnot's theoretical framework with the painstaking experimental gas measurements published by French scientist Regnier in 1847, and out of that combination came a proposal for a genuinely absolute temperature scale, one with a real 0 point rather than an arbitrary reference point like the freezing temperature of water, which is, after all, only special to us because we happen to live surrounded by liquid water. Thomson's calculation placed that 0 point at roughly -273 degrees Celsius. The modern accepted figure, refined by a century and a half of steadily improving instruments, is -273.15 degrees Celsius, which means a physicist working with slide rules and mercury thermometers in the 1840s landed within a fraction of a degree of a value we'd only nail down with real precision generations later. That's worth sitting with for a second, because it's easy to gloss past just how remarkable that accuracy was, given the tools available to him. In his own writing, Thomson described this point as one which cannot be reached at any finite temperature, however low, a phrase that, in hindsight, reads almost like a prophecy of the third law of thermodynamics, a law that wouldn't be formally stated for another 58 years. The scale Thomson proposed eventually took his name, becoming what we now call the Kelvin scale, and in 1892, Thomson himself was elevated to the British peerage as Baron Kelvin, making him, by most accounts, the first scientist ever raised to the House of Lords purely on the strength of scientific achievement rather than birth or politics. Alongside German physicist Rudolf Clausius, working through the 1850s, Thomson also helped develop the second law of thermodynamics, the law that explains why heat always flows from hot to cold and never spontaneously reverses itself, and which, when applied to engines specifically, produces what's known as the Kelvin-Planck statement. No engine, no matter how cleverly designed, can ever convert 100% of the heat it absorbs into useful work. Some of it always unavoidably escapes as waste, so by the middle of the 19th century, physics had its flaw. 0 Kelvin. Absolute zero, a number below which, according to everything anyone understood about the physical world, nothing could possibly exist. But defining a flaw and proving you can never actually stand on it are two separate problems, and it would take another half-century before anyone formalized, with real mathematical rigor, exactly why that floor was not just extremely cold, but genuinely, permanently unreachable. The third law, why you can never actually get there. That formalization came from a German chemist named Walter Nernst, and the year was 1906. Nernst's contribution became known as the third law of thermodynamics, and its modern statement reads something like this: "It is impossible, by any procedure, no matter how idealized, to reduce any system to the absolute zero of temperature in a finite number of operations." 6 years later, in 1912, responding to objections raised by none other than Albert Einstein, Nernst sharpened his own phrasing, stating plainly that the absolute zero point cannot be reached. Physicist Simon would later crystallize this into what's now called the principle of unattainability of absolute zero, a name that does a pretty efficient job of summarizing the whole idea in 4 words, even if it doesn't tell you why. Here's the intuition behind it, stripped of the equations, because the equations aren't the point of this video, the strangeness is. Imagine trying to cool something down as a series of discrete steps, where each step removes a bit more energy and nudges the system a bit closer to zero. The third law says that no matter how many of these steps you perform, you can only ever get closer, asymptotically, the same way a curve on a graph gets closer and closer to a line without ever quite touching it, no matter how far you extend the graph. Each additional increment of coldness demands more effort than the last, and actually reaching the floor would require, in a sense, an infinite number of these ever more demanding steps, stacked one after another forever. You can get achingly, absurdly close, closer than most of us can meaningfully picture. You cannot arrive, not with better equipment, not with more time, not ever. It's worth pausing here on a subtlety, because physicists themselves don't treat this as a completely closed, tidy case with no loose threads. Some modern theoretical papers draw a careful distinction between the third law strictly defined, which Nernst tied specifically to slow, quasi-static, so-called adiabatic cooling processes, and the broader unattainability principle, which is thought to rule out reaching absolute zero by any finite physical means whatsoever, adiabatic or not. There's ongoing technical discussion, mostly confined to specialist journals nobody outside physics departments will ever read, about whether some exotic, non-adiabatic method might someday be treated differently in the underlying mathematics, even if, in every experiment ever actually performed, absolute zero has never once been reached, and nobody seriously expects that to change. That distinction matters enormously for theorists arguing about the fine print of the law. For our purposes, and for every laboratory result we're about to walk through, the practical outcome is exactly the same either way. Nobody has ever gotten there. Which raises the obvious next question, and it's the question this video is actually going to spend most of its remaining time on. If 0 Kelvin can genuinely never be touched, how close have humans actually managed to get? And what strange things have happened to matter along the way, on the long, difficult climb down toward that unreachable floor? Because it turns out, the story of getting close to absolute zero is just as strange as the story of the negative temperature loophole we opened this video with, maybe stranger, and it deserves its own careful walkthrough before we get back to the paradox waiting at the end. Before Bose-Einstein condensates, the earlier chapters of the Cold War against zero, most popular science coverage of ultra-cold physics jumps straight from Lord Kelvin in 1848 to Bose-Einstein condensates in 1995, as if nothing happened in the century and a half in between. That's a shame, honestly, because some of the strangest, most delightful physics in this entire story happened in that gap, in labs across Europe and North America, decades before anyone had the technology to cool a gas with lasers. So let's slow down here and walk through it properly, because these earlier discoveries aren't just historical trivia. They built the tools, the intuitions, and in some cases, the literal physical techniques that everything after 1995 depended on. The story really begins with a Dutch physicist named Kamerlingh Onnes, born in Groningen, the Netherlands, on September 21, 1853, and working for most of his career at the University of Leiden. Onnes had a near-obsessive commitment to precise, careful measurement, and he spent years perfecting the equipment needed to liquefy increasingly stubborn gases. On July 10, 1908, in his laboratory at Leiden, Onnes became the first person in the world to successfully liquefy helium, a gas that resists turning liquid until it's cooled to somewhere around 4 degrees above absolute zero, colder than almost anything else known at the time. He later described that day as the most glorious moment of his career, and it's easy to understand why. For the next 15 years or so, until roughly 1923, Leiden was the only laboratory anywhere on Earth with access to liquid helium, meaning it was, quite literally, the only place in the world where physicists could run experiments below about 14 Kelvin. That achievement alone earned Onnes the Nobel Prize in Physics in 1913. But Onnes wasn't finished, and what happened 3 years after the helium breakthrough turned out to matter even more. On April 8, 1911, Onnes and his collaborators were testing the electrical resistance of a solid mercury wire, immersed in a bath of that hard-won liquid helium, expecting to see resistance gradually decline as the temperature dropped, the way it does in ordinary metals, cooled towards zero. Instead, at 4.2 Kelvin, the resistance didn't decline gradually at all. It vanished, suddenly and completely, dropping to zero as if a switch had been flipped. Onnes wrote in his notebook that mercury had passed into a new state, one that, on account of its extraordinary electrical properties, might be called the superconductive state. He first called the effect supraconductivity, before eventually settling on the name we still use today, superconductivity. It's a genuinely strange thing to picture, a loop of wire that could, in principle, carry an electrical current around and around forever, with no power source continuously feeding it, because there's simply nothing left to slow the current down. By multiple historical accounts, this discovery came as a complete surprise, an accident born out of careful measurement rather than a targeted search, which somehow makes it more impressive rather than less. And here's a detail that tends to get lost in the retelling, one worth pulling out specifically, because it connects directly back to a phenomenon we're about to spend real time on. On that exact same day, April 8, 1911, while pushing his equipment toward its coldest possible temperature, around 1.8 Kelvin, Onnes separately noted something odd happening in the helium bath itself. He wrote that just before the lowest temperature was reached, the normal boiling of the liquid helium suddenly stopped, replaced instead by a strange, quiet evaporation in which the liquid visibly shrank. Historians now recognize this offhand notebook entry as the very first observation of superfluidity, a phenomenon that wouldn't actually be identified, understood, and properly named for another 27 years. Onnes had stumbled onto two of the strangest phenomena in all of condensed matter physics on the exact same afternoon, and only fully grasped the significance of one of them. Onnes kept pushing after that too, spending years trying to squeeze his liquid helium bath even colder, using an increasingly enormous battery of pumps to reduce the pressure above the liquid and, with it, its boiling point. By the mid-1920s, he'd gotten down to somewhere around 0.7 Kelvin, and, reasonably enough given what he knew at the time, he predicted that this would remain the coldest temperature achievable in any laboratory on Earth, since there was no other known element with a lower boiling point than helium waiting in reserve. He turned out to be wrong, and the reason he was wrong arrived that same year, from an entirely different direction. In 1926, two physicists, Peter Debye and William Geoch, working independently of each other and apparently unaware they were chasing the same idea, proposed a cooling method that didn't rely on boiling anything at all. Their technique, which came to be called adiabatic demagnetization, worked with what's known as the magnetocaloric effect. Take a paramagnetic salt, magnetize it while it's in contact with a cold bath, which aligns its internal magnetic moments and releases a bit of heat into that bath, then isolate the salt thermally and switch the magnetic field off. As the moments inside the salt randomize themselves again, no longer held in alignment by the field, the sample's temperature drops, and it drops below where it started. It took 7 years for anyone to actually build the thing and prove it worked. But in 1933, Geoch, working with collaborator D. P. McDougall, used a sample of gadolinium sulfate to cool matter below 1/4 degree above absolute zero, the first time anyone had ever pushed a laboratory sample below a full Kelvin. A separate European team, working independently, reached a very similar temperature at almost exactly the same time. Refinements of the same basic technique kept pushing the record down over the following decades, reaching roughly 2 millikelvin, 0.002 of a degree, by 1953. Adiabatic demagnetization is still used today, particularly in space-based instruments, precisely because, unlike some of the techniques we're about to cover, it doesn't depend on scarce, expensive helium-3 and can be built into a relatively compact package. That second phenomenon, superfluidity, finally got its proper discovery in 1937, and it's a story with a fair amount of quiet drama buried inside it. A Soviet physicist named Pyotr Leonidovich Kapitsa, born in Kronstadt in 1894, had lived through genuine tragedy, losing his first wife and 2 young children to an influenza epidemic in 1921, after which he relocated to Cambridge, England, to work with Ernest Rutherford at the Cavendish Laboratory, before eventually returning to Moscow. In 1937, back in his own laboratory, Kapitsa measured the flow of liquid helium through an almost impossibly narrow gap, just half a micron wide, between 2 closely spaced disks. Below a specific temperature threshold called the lambda point, the helium simply poured through that gap with almost no resistance at all, flowing in a way that shouldn't have been physically possible for an ordinary liquid to manage. And in a genuine coincidence of independent discovery, 2 other physicists, John Allen and Donald Misner, working separately at Cambridge's Mond Laboratory, were running their own experiments on helium flow through narrow capillary tubes at essentially the same time, and found the exact same astonishing near-frictionless behavior. Both results were published side by side, back to back, in the journal Nature on January 8, 1938. Kapitsa had submitted his paper first, on December 3 of the previous year. Allen and Misner followed 19 days later. It was Kapitsa's paper that gave the phenomenon its lasting name, describing helium below the lambda point as entering a special state that he suggested calling a superfluid. What does superfluid helium actually do? It flows with essentially zero internal friction, zero viscosity, meaning it doesn't resist its own motion the way every ordinary liquid does. In demonstration footage, and it's genuinely worth searching for if you've never seen it, superfluid helium appears to defy gravity outright, creeping up and over the inside walls of its own container in an impossibly thin film, and dripping down the outside, as though the liquid were actively trying to escape. It can leak through microscopic pores and gaps that would stop any conventional liquid dead in its tracks. The theoretical explanation for why any of this happens came a few years later, between 1940 and 1941, from a 29-year-old Soviet theoretical physicist named Lev Landau, who introduced an entirely new conceptual tool into physics called the quasi-particle, a way of describing collective, wave-like disturbances moving through the superfluid as if they were particles in their own right. Landau's theoretical work earned its own separate Nobel Prize in 1962. Kapitsa, for his part, received the Nobel Prize in Physics in 1978, a full 41 years after the original 1937 discovery, an unusually long gap by Nobel standards, awarded specifically for his basic inventions and discoveries in the field of low-temperature physics. And here's the quiet injustice tucked into this whole story, the kind of detail that historians of science like to point out. Allen and Misner, despite discovering essentially the same phenomenon at essentially the same moment through an entirely independent experimental route, never received any share of that prize at all. If superfluid helium-4 sounds strange enough on its own, its rarer isotope cousin, helium-3, missing a single neutron compared to ordinary helium, turned out to be even stranger, and getting it to reveal its secrets took physicists another 3.5 decades of trying. Here's the underlying reason why helium-3 was so much harder to crack. Helium-4 is what's called a boson, a category of particle that's relatively willing to condense into a single collective quantum state, which is part of why it becomes superfluid at the comparatively warm temperature of about 2.17 Kelvin. Helium-3, on the other hand, is a fermion, and under the ordinary rules governing fermions, they're not supposed to condense together the same way at all. They're built to avoid occupying identical states. Shortly after 1957, when physicists John Bardeen, Leon Cooper, and John Schrieffer published their landmark BCS theory explaining ordinary electrical superconductivity, other physicists began speculating that fermions might still find a workaround, pairing up into what are called Cooper pairs. two fermions bound together tightly enough that the pair, as a unit, starts behaving like a boson and can then condense the way bosons do. If that mechanism held for electrons inside a superconducting metal, the thinking went, maybe something similar could happen for helium-3 atoms too. The search for helium-3 superfluidity dragged on for roughly a decade with nothing to show for it, and by around 1970, David Lee, one of the physicists working on the problem at Cornell University's low-temperature physics laboratory, later described the mood among researchers in the field as one of genuine gloom and pessimism. Part of what had been holding the field back was simply a lack of the right machine. Back in 1951, a physicist named Heinz London had proposed, on paper, a genuinely new way to refrigerate matter continuously, rather than in the one-shot bursts that techniques like adiabatic demagnetization required. Mix liquid helium-3 into liquid helium-4 and exploit the fact that, below a certain temperature, the two isotopes naturally separate into two distinct layers, one rich in helium-3 and one dilute. Forcing helium-3 atoms to cross from the concentrated layer into the dilute one costs energy that has to be pulled from the surroundings as heat, in a process that behaves thermodynamically almost like evaporation, except that, because the helium-4 never actually boils away, the whole cycle can in principle keep running indefinitely. It took 14 years for anyone to actually build a working version of London's idea. In 1965, a team at Leiden University, Das, De Bruyn-Ubota, and Taconis, working, fittingly, in the very same laboratory tradition Kamerlingh Onnes had founded half a century earlier, built the first working dilution refrigerator and reached 220 millikelvin, the coldest liquid helium had ever been pushed at that point. And then, on April 20, 1972, everything changed in a single afternoon, in a lab equipped with exactly this kind of ultra-cold refrigeration technology. A graduate student named Douglas Osheroff, working under Lee and fellow physicist Robert Richardson at Cornell, was cooling a sample of helium-3 down into the millikelvin range, thousandths of a degree above absolute zero, using a specialized cooling method originally proposed by the Soviet physicist Pomeranchuk, when he noticed something odd in his measurements, small anomalies that shouldn't have been there according to anything anyone expected. Careful follow-up work revealed the astonishing truth. Below about 3 millikelvin, liquid helium-3 does indeed become superfluid, exactly as theorists had speculated it might, 15 years after the BCS theory first suggested it was possible. But it turned out to be even stranger than anyone had predicted. Rather than a single superfluid phase, helium-3 revealed not one, but three distinct superfluid phases, each with zero viscosity, each magnetically active, and each exhibiting bizarre, direction-dependent behavior that had simply never been observed in any physical system before. Lee, Osheroff, and Richardson shared the Nobel Prize in Physics in 1996 for the discovery, and physicist Anthony Leggett, who helped work out the underlying theory of these new phases, later called superfluid helium-3, the most sophisticated condensed matter system that physicists can genuinely claim to understand in quantitative detail, which is a remarkable thing to be able to say about a substance discovered essentially by accident in a graduate student's routine measurements on one particular afternoon in April. There's one more crucial piece of this pre-1995 story, and honestly, it might be the single most important piece of all, because without it, essentially nothing in the rest of this video would have been possible. All of the cryogenic techniques we've covered so far, liquid helium baths, careful thermal insulation, clever mechanical refrigeration, share a common limitation. They cool things down by physically removing heat through contact with something colder, and there's only so cold you can push that approach before it simply runs out of headroom. What changed the entire field? What actually opened the door to the nanokelvin and picokelvin regimes we'll spend the rest of this video exploring was something conceptually different altogether, using light itself, specifically laser light, to slow atoms down almost to a standstill. The technique is called laser cooling, and its development runs through the 1980s, largely across three research groups working somewhat independently before eventually converging. In 1985, physicist Stephen Chu, working at Bell Laboratories in Holmdel, New Jersey, set up an experiment using 6 laser beams, arranged in 3 opposing pairs, pointed along 3 perpendicular axes, all tuned so that any atom trying to move in any direction would be gently pushed backward by the light hitting it head-on. The effect, applied to a small cloud of roughly 1 million sodium atoms, was to slow them down dramatically, trapping them in what Chu, borrowing an image from everyday life, nicknamed optical molasses, because the resistance the light exerted on the atom's motion resembled the way a marble slows down as it sinks through a thick, viscous syrup. This specific approach, called Doppler cooling, brought that cloud of sodium atoms down to roughly 240 microkelvin, an already remarkable achievement, and Chu built on it further, constructing what's called a magneto-optical trap, adding magnetic fields into the mix so the cooled atoms could actually be held in place against gravity for extended study, rather than just slowed down momentarily. His work built partly on earlier research from a Bell Labs colleague, Arthur Ashkin, who had pioneered using focused laser light to physically trap small particles in the first place. Meanwhile, physicist William Phillips, working at the National Institute of Standards and Technology in Gaithersburg, Maryland, developed careful new methods for actually measuring the temperature of these laser-cooled atom clouds with precision, including a clever technique where the atoms were allowed to fall freely under gravity after the trapping lasers switched off, passing through a thin sheet of measuring laser light on the way down, with the spread and timing of that fall revealing the cloud's temperature. And in 1988, using this method, Phillips discovered something that nobody in the field expected and that initially seemed almost impossible. His atom clouds had reached temperatures as low as 40 microkelvin, a full 6 times colder than the theoretical Doppler limit, a flaw that Doppler cooling, according to the physics everyone understood at the time, simply should not have been able to cross. For a moment, this looked less like a discovery and more like a measurement error. It wasn't. The explanation arrived almost immediately, worked out independently by physicist Claude Cohen-Tanouji of the École Normale Supérieure in Paris, working with colleague Jean Dalibard, and confirmed by Chu's group at Stanford, where Chu had since relocated. It turned out the original theoretical calculation of the Doppler limit had assumed an unrealistically simplified model of the atom, one with just 2 energy levels, when real sodium atoms actually possess several additional sublevels that Doppler theory alone hadn't accounted for. Once those extra sublevels were factored in, a subtler cooling mechanism emerged, one that Cohen-Tanouji and Chu's teams named Sisyphus cooling, borrowing the name of the mythological figure condemned to eternally push a boulder uphill only to watch it roll back down. In Sisyphus cooling, atoms are repeatedly forced to climb tiny potential energy hills, created by the shifting polarization of the laser light as they move through it, losing a small amount of kinetic energy each time they crest one of those hills, over and over, cooling further with every repetition. Cohen-Tanouji's group pushed the technique even further that same year, demonstrating one-dimensional cooling all the way down to 2 microkelvin, a result that broke through yet another theoretical flaw, this one called the recoil limit, previously assumed to be an absolute barrier as well. Chu, Cohen-Tanouji, and Phillips shared the Nobel Prize in Physics in 1997 for developing methods to cool and trap atoms using laser light, and it's genuinely hard to overstate how much downstream physics depended on their work. Every single ultra-cold result covered in the rest of this video, the Bose-Einstein condensates of 1995, the pico-Kelvin records set at MIT and later in Germany, and the negative temperature experiment we'll get to shortly, all of it rests directly on techniques worked out in laser physics labs across the 1980s in New Jersey, Maryland, and Paris. And beyond the pure research value, this same line of work quietly reshaped everyday technology too. Laser cooling techniques led directly to atomic clocks, roughly 100 times more precise than what came before. Clocks that now sit at the heart of GPS satellite navigation and deep space mission tracking. So the next time your phone tells you, with unsettling confidence, exactly which street you're standing on, you're indirectly relying on physics first worked out by researchers trying to make atoms sit as still as possible, using nothing but carefully tuned beams of light. With all of that groundwork properly laid, the mechanical refrigeration of Kamerlingh Onnes, the accidental superfluid discoveries of Kapitsa and of Lee, Osheroff and Richardson, and finally, the laser cooling breakthroughs of Chu, Cohen-Tanouji, and Phillips, we're now in a position to properly appreciate what happened next. The moment, in 1995, when two separate research teams finally used all of these accumulated tools together to produce a state of matter that had existed, until that point, only as a 70-year-old theoretical prediction, the race to the bottom. The modern chapter of this story starts in 1995, and it starts with two separate research groups racing toward the same finish line using two closely related approaches, both built on the laser cooling foundation we just walked through. One team worked at the University of Colorado at Boulder, led by physicists Eric Cornell and Carl Wieman. The other worked across the country at MIT, led by Wolfgang Ketterle. Both groups were chasing a theoretical prediction made decades earlier by Albert Einstein and the Indian physicist Satyendra Nath Bose. A prediction that said if you cooled a dilute gas of certain kinds of atoms low enough, the individual atoms would stop behaving like a crowd of independent particles bouncing around at random, and instead collapse into a single, unified quantum state, moving in perfect lockstep, as if the entire gas had somehow become one enormous atom, sharing a single quantum identity. In 1995, both teams succeeded, cooling atomic gases below 1 microkelvin, 1/1,000,000th of a degree above absolute zero. One account puts the Colorado team's actual condensate at 170 nanokelvin, a temperature so far removed from anything in ordinary human experience that most comparisons stop being useful at all. What they'd created was a genuinely new state of matter, joining solid, liquid, gas, and plasma on the list science teachers hand out, the fifth entry, the Bose-Einstein condensate. 6 years later, in 2001, Cornell, Wieman, and Ketterle shared the Nobel Prize in Physics for the discovery, and in the years that followed, cooling atomic gases into the nanokelvin range became almost routine across labs worldwide, a technique taught to graduate students rather than treated as a frontier, with 3 nanokelvin standing as something close to the baseline record before the next major leap arrived. That leap came in September of 2003, back at MIT, where a team including researchers Aaron Lienhardt and Tom Pasquini, working under physics professor David E. Pritchard, a pioneer in the field of atom optics, managed to cool a cloud of sodium gas down to 500 picokelvin, half of 1/1,000,000th of a degree above absolute zero. That's roughly 6 times colder than the previous nanokelvin scale record, and it marked the first time any gas had ever been cooled below the 1 nanokelvin threshold at all, a genuine milestone rather than a marginal improvement. The work was funded by NASA, and it came with a practical complication that's easy to overlook if you've never thought carefully about what cold actually requires at this scale. At temperatures this extreme, you simply cannot keep your sample inside an ordinary container because the atoms would instantly stick to the walls the moment they touched anything solid, and there is, in any case, no known container material that could itself survive being cooled to such a temperature without its own atomic structure falling apart in some way. Instead, these gases have to be suspended entirely by magnetic fields, floating in space inside the apparatus, touching absolutely nothing at all. Separately, researchers at the National Institute of Standards and Technology in Boulder, Colorado, using a battery of specialized lasers, an obvious continuation of Phillips's own earlier work at that very institution, pushed a different kind of record to 36 microkelvin, a benchmark that stood for a time as a useful point of comparison in later coverage of the field, even as the picokelvin scale results from MIT represented the genuinely extreme frontier by then. The record that stands today, as far as the sources compiled for this video can confirm, was set in August of 2018 and formally published in the journal Physical Review Letters on August 30th, 2021. It came from the Qantas collaboration, a team spanning several research institutions in Germany and 2 in France, and the number they achieved was 38 picokelvin, 38 trillionths of a single degree above absolute zero. To get there, the team first laser-cooled and evaporatively cooled a cloud of rubidium atoms down to roughly 2/100000ths of a degree above absolute zero, forming a Bose-Einstein condensate in the same broad family of quantum states first produced back in 1995. Then came the genuinely clever part, the part that separates this experiment from simply doing the same thing, but trying harder. Rather than attempting to cool the sample further through conventional means, the researchers dropped the entire apparatus down the Bremen Drop Tower, a facility connected to the European Space Agency, 120 meters, roughly 393 feet, straight down, in order to create a brief window of genuine microgravity. Under normal gravity, an ultra-cold atom cloud tends to sag and spread in ways that generate small amounts of residual heating, an unavoidable side effect of the cloud simply falling under its own weight inside the trap. Strip gravity out of the picture entirely, even for just a few seconds, and that particular source of heating disappears altogether. Combined with a technique called time-domain matter-wave lensing, using a cylindrical magnetic lens to further compress the cloud's spread in 3 dimensions as it fell, the team managed to hold their sample at 38 picokelvin for about 2 seconds during the drop. And here's a detail that gives you some sense of how much further this general approach could theoretically go, if given the chance. The researchers said that under conditions of true, sustained weightlessness, the kind you'd only get in orbit rather than a 120-meter drop tower on Earth, they believe they could maintain that record-breaking chill for as long as 17 seconds straight. That 38 picokelvin figure is currently recognized by Guinness World Records as the lowest artificial temperature ever achieved by anyone, anywhere. It's worth sitting with that number for a second, because the scale of it is genuinely hard to internalize, even once you've heard it stated plainly. 38 trillionths of 1 degree above absolute zero. To really appreciate how small that is, we need one more comparison, and it means taking a short detour into radio astronomy, because it turns out the universe itself has a background temperature, one that was discovered almost completely by accident in New Jersey in the mid-1960s. In 1964, 2 radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs using a large, horn-shaped antenna that had originally been built for satellite communication, bouncing early signals off the Echo balloon satellites and later the Telstar satellite. Once that antenna was free for other use, Penzias and Wilson pointed it at the sky to make careful radio measurements, initially of a supernova remnant. And no matter what they did, they kept picking up a faint, persistent hiss, a uniform noise signal, coming from every direction in the sky at once, at every hour of the day and every season of the year, refusing to go away. They spent months troubleshooting, checking cables, checking electronics, and, in a detail that survived in the retelling precisely because it's so wonderfully mundane, they eventually climbed up into the horn antenna itself and physically removed a pair of nesting pigeons, along with the accumulated droppings the birds had left behind, on the reasonable suspicion that the mess might be the source of the interference. It wasn't. The signal stayed exactly where it was, at a steady few degrees above absolute zero, no matter what they cleaned out or ruled out. What Penzias and Wilson didn't know, at least not yet, was that a team of physicists just down the road at Princeton University, led by Robert Dick, was actively trying to build equipment to search for exactly this kind of signal, based on a theoretical prediction that radiation left over from the early universe should still be detectable today, redshifted and cooled by billions of years of cosmic expansion. Once the 2 groups connected, the picture snapped into focus immediately. Dicker reportedly turned to his own team and said, simply, "Well, boys, we've been scooped." What Penzias and Wilson had stumbled onto, without setting out to look for it, was the afterglow of the Big Bang itself, the cosmic microwave background, radiation that has been traveling through space since the universe was only a few 100,000 years old, now stretched by billions of years of expansion down to a steady, uniform temperature of about 2.7 Kelvin. It remains, to this day, one of the strongest single pieces of evidence supporting the Big Bang model of the universe's origin, and it settled a genuine scientific argument of the era in the process, tipping the balance decisively away from a rival idea called the steady-state theory, which held that the universe had no beginning at all. Penzias and Wilson shared the 1978 Nobel Prize in Physics for the discovery, and, in a small coincidence worth pausing on given everything else in this video, they shared that particular year's prize with a name we've already spent real time on, Piotr Kapitsa, honored that same year for his own decades-old discovery of superfluid helium. So that's the number to hold on to, 2.7 Kelvin, the background hum of the entire universe. present in every direction you could possibly point a sensitive enough antenna. And it's worth pausing on exactly what Penzias and Wilson had originally pointed that antenna at, because the patch of sky they happened to be observing turns out to matter for one more thread in this story. The object they'd been calibrating their equipment against was the Cassiopeia A supernova remnant, the leftover debris cloud from a massive star that exploded roughly 3 centuries ago. Decades later, long after Penzias and Wilson had moved on with their Nobel Prize, astronomers pointed a very different kind of instrument, NASA's Chandra X-ray Observatory, at that exact same patch of sky and found something else remarkable hiding inside it. A neutron star, the collapsed core left behind by that same long-ago explosion, and the youngest neutron star ever found in our galaxy. Watching it across a series of observations taken over roughly a decade, astronomers noticed its surface temperature dropping faster than any standard cooling model could explain. In 2011, a team of researchers proposed a genuinely striking explanation. The neutrons packed into that star's core, crushed to a density roughly 1 trillion times anything achievable on Earth, had recently begun transitioning into a superfluid state, the very same basic phenomenon Kapitsa first identified in a beaker of liquid helium back in 1937, only now playing out under conditions no laboratory on Earth could ever hope to replicate. That transition, researchers argued, triggers a burst of neutrino emission that temporarily speeds up the star's cooling, and it stands as the first direct evidence that superfluidity, a phenomenon we've spent real time on in this video, as something delicate enough to require a 120-meter drop tower or an ultra-pure lab crystal, also occurs naturally, on its own, inside the crushed heart of a dead star. One patch of sky, one antenna pointed at it by accident in 1964, one X-ray telescope pointed at it deliberately decades later, and 2 completely unrelated headline discoveries about the physics of extreme cold and extreme density, sitting on top of each other in the same small corner of the constellation Cassiopeia. Now compare that to the coldest naturally occurring place we actually know of anywhere in the observable universe. The Boomerang Nebula, a cloud of gas roughly 5,000 light-years away in the constellation Centaurus, which the European Space Agency measures at an average temperature of about -272 degrees Celsius, roughly 1 full Kelvin. 1 Kelvin sounds impressively cold until you realize it's colder than that 2.7 Kelvin background hum left over from the Big Bang, meaning the Boomerang Nebula has somehow found a way to undercut the ambient temperature of the entire universe around it, a genuinely strange trick for a nebula to pull off. And yet, next to a laboratory in Germany producing 38 picokelvin, the coldest known natural location in the entire universe looks almost balmy by comparison. Embarrassingly warm, even. For one more point of comparison, consider the coldest object ever confirmed to exist beyond our own solar system, a brown dwarf, essentially a failed star, catalogued as WISE 0855, discovered in 2014 using NASA's WISE space telescope, sitting just over 7 light-years from Earth, close enough to be one of our nearest stellar neighbors. Depending on which study you consult, its temperature comes out somewhere in the range of roughly 250 to 285 Kelvin, meaning that even the coldest object anyone has ever found outside our own solar system, studied with instruments as advanced as the James Webb Space Telescope, is still warmer than Jupiter, whose own average temperature sits at about 130 Kelvin. Humans, working with lasers, magnets, and a 120-meter drop tower, have outcooled the universe itself, outcooled the coldest known natural object floating anywhere inside it, and outcooled the coldest failed star we've ever pointed a telescope at least within the tiny, fleeting confines of a 2-second experiment conducted on a Tuesday in Bremen. None of these numbers, though, no matter how small, ever actually reach zero. They approach it exactly the way the third law predicted they would, getting closer and closer without ever crossing the line, generation after generation of physicists inching the record downward by a few more decimal places. Which brings us, finally, back to the part of this story where things stop making intuitive sense entirely, the reason we started this video in the first place. The paradox. When colder isn't the right word anymore. Here is where we have to be careful, because this is the point in the story where a lot of casual explanations of this topic quietly get the physics wrong, and it's worth taking the extra time to get it right, because the actual truth turns out to be stranger and more interesting than the misconception it so easily gets mistaken for. Since 1951, a handful of laboratory experiments have produced systems that physicists describe, using completely standard, peer-reviewed terminology, as having negative absolute temperature. On paper, a system with a temperature of, say, -1 Kelvin would appear to sit below the 0 mark on the Kelvin scale, the exact same mark that Lord Kelvin defined as an unreachable floor back in 1848, and that Nernst's third law explicitly forbids anyone from ever crossing. So did these experiments actually break the third law? Did physicists somehow manage to create something colder than physically possible? Something below the floor of the universe? No. And the reason why is the single most counterintuitive fact in this entire video, so it deserves to be stated plainly, more than once, in more than one way, because it runs directly against the instinct that the phrase negative temperature naturally builds inside your head the moment you hear it. A negative temperature system is not colder than absolute zero. It is hotter than any positive temperature that exists, including infinite temperature. As Ulrich Schneider, one of the physicists behind the most famous of these experiments, put it directly, the inverted distribution that defines negative temperature is not colder than 0 Kelvin, but hotter than any positive temperature at all, because the temperature scale in these very specific, carefully engineered systems doesn't simply end at infinity the way you might reasonably expect it to. Instead, it wraps around and jumps to negative values that represent an even more extreme, even hotter regime than anything positive temperatures could ever describe, no matter how high you push them. To understand why that's actually true, and not just a clever semantic trick physicists use to make a mundane result sound more exciting, you need to understand what temperature is really counting underneath the surface, in terms of how particles distribute their energy across all the states available to them. In an ordinary, everyday system, the vast majority of particles sit in low-energy states, and progressively fewer and fewer particles occupy higher and higher energy states, tapering off gradually, the way a bell curve tapers off toward its edges. Physicists call this pattern the Boltzmann distribution, and it holds true for gases, for solids, for basically everything you've ever touched, felt, or measured a temperature on in your entire life. Turn the heat up on any of these systems, and the curve shifts. More particles migrate into higher energy states than before, but the fundamental shape, most particles low, fewer particles high, never actually flips over, no matter how hot you make it. Negative temperature describes a system where that shape flips completely, upside down. Instead of most particles occupying low energy states, most particles occupy the highest energy states available to them, with progressively fewer particles sitting down in the lower energy states. The exact mirror image of everything we just described. It's the Boltzmann distribution turned on its head, a genuinely inverted population. And that inversion is only possible in the first place because these particular systems have something that ordinary systems simply don't have: an upper limit on how much energy any individual particle is allowed to have. Just as an ordinary system has a lower boundary, since particles obviously can't have less than 0 kinetic energy, no matter how you slice it, these special engineered systems have a ceiling as well, sitting up at the top, and it's that ceiling, that hard upper bound, that makes the whole strange inversion mathematically possible in the first place. Picture temperature not as a straight number line running from negative infinity all the way out to positive infinity, the way we normally, intuitively imagine number lines working when we're taught about them in school. Picture it instead as something closer to a loop, a closed circle rather than an open line. As an ordinary positive temperature system gets hotter and hotter, it approaches what you'd call infinite temperature, the theoretical point at which particles are distributed with total, complete indifference across every available energy state. No preference at all for low over high. In a normal system, one that's unbounded above, with no ceiling on energy, you just keep climbing steadily toward that infinite temperature limit and never actually get anywhere past it, since there's genuinely nowhere past it to go. But in a bounded system, one built with a hard energy ceiling, once you push past that point of total indifference and start piling more particles into the highest energy states than the lowest ones, you don't stay on the positive side of the number line at all. You flip, all at once, to the negative side, and paradoxically, that negative side represents states that are even hotter than positive infinity itself, a genuinely strange thing for a number to be. The coldest a negative temperature system can theoretically be, in this bizarre inverted framework, is what's sometimes called negative zero, the point where the inversion becomes essentially total and complete. And even that state, the coldest negative temperature imaginable, is still hotter than every single positive temperature that exists anywhere in ordinary physics. Negative temperatures, in other words, aren't a new basement built somewhere below the ground floor of the temperature scale. They're a penthouse, built on top of the roof, accessible only by a strange, narrow staircase, and one that only exists at all for buildings, so to speak, that were specifically constructed with an upper limit on how many floors they're allowed to have in the first place. The first experiment, a crystal, a magnet, and Harvard, 1951. The very first person to demonstrate this experimentally wasn't chasing negative temperature for its own sake, at least not initially, not as the goal he set out with that morning. His name was Edward Mills Purcell, and working alongside colleague Robert V. Pound at the Department of Physics at Harvard University, he published a short paper in January of 1951 in the journal Physical Review, titled simply, "A Nuclear Spin System at Negative Temperature." The paper ran barely 2 pages, from page 279 to page 280, remarkably brief for an idea that would echo through physics for the next 70 years and counting, still being argued about in journals today. Purcell had earlier discovered something quietly useful about a particular material. Sufficiently pure crystals of lithium fluoride display nuclear spin relaxation times, at room temperature, on the order of whole minutes. That might not sound remarkable on its own, until you compare it against the timescale on which the nuclear spins inside that same crystal actually interact with one another, which is roughly 10 to the -5 seconds, 100,000th of a second, an almost unimaginably brief interval by comparison. That massive gap, minutes on one side, fractions of a millisecond on the other, meant physicists could treat the nuclear spins as their own isolated little thermodynamic system, one with its own well-defined, physically meaningful temperature, separate and distinct from the temperature of the crystal lattice surrounding it. Purcell and Pound took a lithium fluoride crystal sitting calmly in equilibrium inside a strong external magnetic field, its nuclear spins lined up neatly the way you'd expect them to be. And then, fast, much faster than the timescale on which the spins could naturally respond and rearrange themselves in reaction, they reversed the direction of that magnetic field entirely, essentially instantaneously from the spin's point of view. The spins, caught off guard by the sudden flip, ended up magnetized in the opposite direction from the new field, a configuration that, under ordinary equilibrium physics, shouldn't have persisted for any meaningful length of time at all. But because of that unusually long relaxation time inherited from the crystal's exceptional purity, the inverted state didn't collapse instantly the way you'd expect. It held together, in a genuine, well-defined thermal equilibrium among the spins themselves, for several full minutes, before finally decaying back to the normal, expected orientation. And in that in-between window, that brief borrowed few minutes, the spin system displayed a property that should sound familiar by now, given everything we just walked through. As it lost internal energy, drifting gradually back toward normal, it simultaneously gained entropy, the exact reverse of how ordinary, positive temperature systems behave, where losing energy always means losing entropy too, hand in hand. That reversal, entropy climbing as energy falls, is the precise mathematical fingerprint of negative temperature, and it's what let Purcell and Pound describe their spin system, with full scientific rigor and confidence, as sitting at a genuine negative absolute temperature. Physicist Norman Ramsey is generally credited with taking this experimental result and formalizing the underlying theoretical concept into the shape physicists still use today, decades later. And in a small footnote to the larger story, one worth including for the sheer texture of it, some accounts also credit Purcell, Pound, and Ramsey with demonstrating a related phenomenon that same year, stimulated emission, at a frequency of 50 kHz, corresponding to a wavelength of about 6 kilometers, using this exact same inverted population approach. If that phrase, stimulated emission from an inverted population, sounds vaguely familiar, even if you've never studied nuclear magnetic resonance in any depth, that's because it's the same underlying principle that would later become absolutely central to the invention of the laser and the maser, The very devices that, decades later, would be used to cool atoms down toward absolute zero in the first place. A strange bit of circularity worth noticing. Purcell himself would go on to share the 1952 Nobel Prize in Physics with Felix Bloch, awarded for their broader work developing nuclear magnetic resonance as a technique, the very same technology that today sits quietly at the heart of every MRI machine in every hospital on the planet, something almost nobody being wheeled into one ever thinks about. Purcell was born in Taylorville, Illinois, on August 30, 1912, earned an electrical engineering degree from Purdue in 1933, studied for a year in Karlsruhe, Germany, completed his physics doctorate at Harvard in 1938, spent the Second World War working on radar technology at MIT's Wartime Radiation Laboratory, and returned to Harvard afterward, where the negative temperature experiment would eventually take shape in that small, 2-page paper. He died in 1997, having spent a career quietly redefining what a 2-page physics paper could accomplish, decades before anyone else would push the same idea into a completely different physical regime. For decades after 1951, negative temperature remained something of a curiosity, confined to the specific, somewhat exotic world of nuclear spin systems, systems where the relevant particles interact meaningfully with each other, but are otherwise fairly cut off from their surroundings, isolated enough to have their own separate thermodynamic identity. What nobody had managed to do, for over 60 years, was find a way to produce negative temperature in the actual motion of atoms moving through space, the kind of kinetic energy most of us instinctively picture when we think about heat and cold in the first place, the version of temperature that shows up in every introductory physics class. That changed in 2013, in a laboratory just outside Munich. The 2013 breakthrough, Munich, potassium, and a crystal made of light. The team was led by physicists Ulrich Schneider and Emanuel Bloch, working across 2 connected institutions in Germany, the Ludwig-Maximilians-Universität in Munich and the Max Planck Institute of Quantum Optics in nearby Garching. Alongside Schneider and Bloch, the full author list on the resulting paper included S. Braun, J. P. Ronsheimer, M. Schreiber, S. S. Hodgman, and T. Rom, and the paper itself, titled Negative Absolute Temperature for Motional Degrees of Freedom, appeared in the journal Science, in volume 339, issue 61115, spanning pages 52 through 55, in January of 2013. That title matters quite a bit, and it's worth unpacking exactly what made this experiment fundamentally different from Purcell and Pound's crystal back in 1951, rather than just a modern repeat of the same trick. Purcell and Pound had achieved negative temperature in the internal spin states of nuclei sitting inside a fixed crystal lattice, an internal, somewhat abstract quantum property that most people never encounter or think about. The Munich team set out to do something that had never once been done before. In 62 years of trying, achieve negative temperature in the actual translational motion of atoms, the literal kinetic energy of particles moving through space, the exact kind of motion that every introductory physics class uses to explain what temperature fundamentally is in the first place. The version of cold and hot that this entire video has been built around from its opening minute. To do it, the team started with a cloud of roughly 100,000 bosonic potassium-39 atoms. Before the experiment even began, this cloud was already among the coldest collections of matter anywhere in the known universe in the ordinary sense, cooled to less than a millionth of a degree above absolute zero, suspended entirely by a careful combination of magnetic fields and laser beams, isolated inside an ultra-high vacuum chamber so that no stray heat from the outside world could sneak in and disturb the delicate setup. The atoms were arranged, initially, so that they repelled one another, and they were held in place using 2 overlapping tools, a dipole trap and an optical lattice, a structure built not out of any physical material at all, but out of standing waves formed by interfering laser beams, a genuine crystal made of light, with a periodic structure just as regular and repeating as the crystal lattice of an actual physical solid. Potassium wasn't chosen because it has any special intrinsic coldness property of its own. Physicists working in this field have been clear and direct about that point whenever asked. It was chosen simply because it happens to be a convenient atom for laser cooling techniques, and because its particular magnetic properties allow researchers to precisely tune the interactions between individual atoms, dialing the force between them from repulsive all the way over to attractive, essentially at will, with a level of control most areas of physics can only dream of. And that tuning was the key to the entire experiment, the single move that made everything else possible. The team took the cloud of atoms, initially repelling each other in that trap and lattice, and flipped the external confining potential, essentially inverting the shape of the trap that had been holding everything in place, while simultaneously switching the interactions between atoms from repulsive to attractive. Under ordinary physics, an attractively interacting gas at negative temperature should be wildly unstable, prone to collapsing in on itself almost immediately, since attraction, combined with high-energy motion and no restoring force, is usually a recipe for the whole system caving in on itself catastrophically. But by carefully bounding the energy spectrum, using the structure of the optical lattice and the shape of the confining potential together, working in concert, the Munich team managed to engineer a final state that was thermodynamically stable against collapse, and stable regardless of how many atoms were involved in the experiment. In other words, they didn't just produce a fleeting, unstable inversion that vanished the instant it appeared. They produced a genuine, if temporary, negative temperature equilibrium state in the actual motion of real atoms moving through real space, for the first time in the 62 years since Purcell and Pound's crystal. Ulrich Schneider summarized the result in a line that's been quoted across nearly every outlet that covered the story at the time. And it's worth repeating here in full, because it's the cleanest possible statement of the entire paradox this video is built around. The inverted Boltzmann distribution, he said, is the hallmark of negative absolute temperature, and that's exactly what the team had achieved. But, he continued, the gas wasn't colder than 0 Kelvin. It was hotter than any positive temperature at all, because in a system like this, the temperature scale doesn't end at infinity the way you'd normally expect it to. It jumps straight to negative values instead. It's a sentence that sounds almost like a riddle the first time you hear it. And honestly, it should, because it's describing a genuinely alien corner of physics that has no real analog anywhere in ordinary human experience. What negative temperature actually unlocks? So what's the actual point of all this? Beyond the sheer strangeness of it, beyond a physicist's curiosity for its own sake. It turns out negative temperature systems aren't just a laboratory curiosity destined to sit in a textbook footnote. They open up some genuinely counterintuitive possibilities, at least on paper, possibilities that ripple outward into engineering and even cosmology. Take heat engines, the kind of machinery that quietly powers most of the modern world. Every ordinary heat engine, the kind that powers a car or a power plant, is bound by a hard efficiency ceiling first described by Sadi Carnot, the very same theorist Lord Kelvin built his absolute scale on top of, back in 1848. That ceiling exists because a heat engine works by drawing energy from a hot reservoir and dumping some leftover waste heat into a colder reservoir, and the colder reservoir, being at a positive temperature, always inevitably absorbs and retains part of that energy, capping how much useful work the engine can ever hope to extract from the process, no matter how cleverly it's designed. But if the hot reservoir happens to sit at a negative temperature instead of an ordinary positive one, the underlying physics shifts beneath your feet, because a negative temperature reservoir, despite the confusing name, is always hotter, in the true thermodynamic sense, than any positive temperature reservoir it could possibly be paired with. That means an engine built around this kind of unusual pairing can, in principle, draw usable energy from both reservoirs simultaneously, rather than losing part of the input to the cold side, the way a conventional engine always inevitably does. The result, according to the physicists behind the 2013 Munich work, is an engine whose measured efficiency can technically exceed 100%. That figure sounds, at first hearing, like it must violate the conservation of energy, and it doesn't, not even slightly. It simply reflects the fact that the usual accounting, one hot source, one cold sink, one hard efficiency ceiling, breaks down entirely once one of your reservoirs is drawing from this exotic, inverted regime that Carnot never had reason to imagine when he first worked out his theorems. There's also a more speculative thread here, one connecting negative temperature to cosmology, the study of the universe on the largest scales imaginable. Physicists involved in the Munich research have noted that the thermodynamic behavior of negative temperature systems shows intriguing parallels to dark energy, the mysterious, still poorly understood phenomenon that appears to be driving the accelerating expansion of the universe itself. That connection is explicitly framed by the researchers as speculative rather than proven, an interesting structural resemblance worth investigating further, rather than a settled mechanism anyone is claiming to have confirmed. But it's part of what made this otherwise niche corner of statistical mechanics interesting to physicists working well outside the ultra-cold atom community, people who study galaxies rather than gas clouds, a millionth of a degree above nothing. Beyond that speculative cosmological angle, negative temperatures are described in the original paper as implying negative pressures, a property that opens entirely new regimes for researchers working with ultra-cold atomic gases, and potentially enables fundamentally new categories of many-body quantum states that simply have no equivalent anywhere on the positive temperature side of the ledger. More broadly still, the underlying platform behind all of this, ultra-cold atomic gases held inside laser-generated optical lattices, has applications reaching well beyond negative temperature specifically, including precision measurement devices, quantum simulations aimed at designing entirely new materials, and altogether new regimes of chemistry that only become accessible at these extremes of cold. The fight over whether any of this is even real now. Here's where the story gets genuinely contentious, and it's a part that a lot of coverage of this topic tends to quietly skip past, because it complicates the clean, tidy, triumphant narrative that's so much easier to tell. Not every physicist agrees that negative absolute temperature, as described across everything we've just walked through, is actually correct. In 2014, physicists Jörn Dunkel and Stefan Hilbert published a paper in the journal Nature Physics with a title that leaves absolutely no ambiguity about where they stood on the question, "Consistent thermostatistics forbids negative absolute temperatures." Their argument, in essence, ran like this. Over the 60-some years since Purcell and Pound, numerous experiments and theoretical papers, including the landmark 2013 Munich result we just spent so much time on, had all relied on a particular mathematical definition of entropy, the one originally developed by Ludwig Boltzmann, the definition taught in essentially every introductory statistical mechanics textbook ever printed. Dunkel and Hilbert argued that this Boltzmann definition, while perfectly useful in most everyday situations, becomes internally inconsistent, both mathematically and thermodynamically, the moment it's applied to systems with a bounded energy spectrum, which is exactly the kind of system where negative temperature is supposed to show up in the first place. Their proposed fix was to switch to a different, older entropy formulation, one originally derived by the American physicist J. Willard Gibbs, but largely overlooked in modern teaching, tucked away in older textbooks nobody assigns anymore. Dunkel himself noted, in comments given to the press around the time, that only a small number of textbooks even teach the Gibbs formula at all, because historically, it simply wasn't considered especially relevant to anything. Once you swap in the Gibbs version of entropy in place of the Boltzmann version, Dunkel and Hilbert argued, the math changes completely. Absolute temperature comes out positive, always, in every case, even for systems with an energy ceiling, which would mean that the negative temperature interpretation applied to decades of experiments, including the celebrated Munich result, was simply a mathematical illusion all along, an artifact of choosing the wrong formula rather than a genuine physical discovery. As a direct consequence, they suggested, the speculative parallel to dark energy that had gotten so much outside attention was probably a dead end too, since there'd be no negative temperature there in the first place to draw the comparison from. That paper did not go unanswered, not even close, and the response from other corners of the physics community was fast, pointed, and unambiguous. Ulrich Schneider himself, alongside colleagues including Stefan Mandt, Akos Rapp, Simon Braun, Hannes Weimer, Emmanuel Bloch, and Achim Roche, several of them co-authors on the original 2013 result, and understandably invested in defending it, published a formal comment directly challenging Dunkel and Hilbert's conclusions, defending the negative temperature interpretation as both mathematically sound and experimentally justified. Dunkel and Hilbert, in turn, published a reply standing firmly by their original position, refusing to budge, and the back and forth didn't stop there, not by a long way. Physicists Dan Frenkel and Patrick Warren separately weighed in with their own paper, arguing that it was actually the Gibbs entropy, the very formulation Dunkel and Hilbert had championed as the supposed fix, that failed a basic sanity check of thermodynamics, the simple, foundational requirement that two objects sitting in thermal equilibrium with each other should always register the same temperature. The Boltzmann entropy, Frenkel and Warren argued, passes that test just fine, and in fact satisfies Dunkel and Hilbert's own stated consistency criterion once you're working with systems large enough to be considered genuinely thermodynamic, rather than the small, somewhat artificial toy examples used in the original critique to make its point. Their conclusion ran directly counter to the paper that had started the whole argument in the first place. Far from being forbidden, they wrote, negative temperatures are inevitable in any system with a bounded energy spectrum. Dunkel and Hilbert replied to that paper too, again standing by their position without backing down an inch, and the discussion continued into further papers over the following years, including a 2015 critique from physicist Jiansheng Wang at the National University of Singapore, which argued that the Dunkel-Hilbert framework fails to satisfy classical thermodynamic postulates laid out decades earlier by theorists Tisser and Callan, and, more strikingly, that under their proposed system, the direction of heat flow between two objects in contact can no longer be reliably predicted just by comparing their temperatures, which most physicists would consider a genuinely serious structural problem for any definition of temperature to carry. A physics blog covering the dispute back in 2014, written by a physicist actively working in the field rather than a science journalist parachuting in from outside, summed up the state of the argument about as honestly as anyone reasonably could. This debate, the author wrote, is far from over, and based on everything gathered for this video, that assessment still seems to hold, years later. What's not in dispute, and this is worth stating clearly so the argument doesn't get overblown, is what actually happened inside the lab, both in 1951 and in 2013. Nobody on either side of this argument is claiming Purcell and Pound's crystal didn't do what the raw data clearly shows it did, or that the Munich team's atoms didn't behave exactly as measured on the instruments. What remains genuinely actively unresolved is a much more abstract, foundational question sitting one level beneath the raw measurements. What is the correct mathematical definition of entropy for a small, bounded, out-of-equilibrium system in the first place? And does that definition genuinely allow for something called negative absolute temperature to exist at all? Or is it, in the end, nothing more than an artifact of picking the wrong formula from the start? It's the kind of argument that can sound almost philosophical from the outside looking in, but for physicists working deep in statistical mechanics, getting these foundational definitions exactly right isn't a side issue to be waved away. It's the whole game. A few more strange corners. Before we bring this back around to the question sitting in the title, it's worth touching on a few more related details that round out just how strange the physics gets down near these extremes. Details that didn't quite fit anywhere else, but are too interesting to leave out entirely. Superconducting magnets, cooled to just a few Kelvin, using techniques that trace directly back to Kamerlingh Onnes' original 1911 breakthrough, quietly power every MRI machine in every hospital that has one, turning laboratory-grade cryogenics into something most of us have personally been wheeled through without giving it a second thought. Modern quantum computers rely on processors chilled down to somewhere between 10 and 15 millikelvin, run continuously by descendants of that same dilution refrigerator first built in Leiden back in 1965, colder even than the deepest depths of interstellar space, just to keep their fragile quantum states from collapsing under ordinary thermal noise. And if you want to see just how far modern engineering has managed to push this kind of continuous industrial-scale refrigeration, there's no better example than a laboratory buried underneath a mountain in central Italy. Deep beneath the Gran Sasso Massif, shielded by hundreds of meters of solid rock, specifically to block out cosmic rays and other background radiation that would otherwise swamp its instruments, an international collaboration of scientists runs an experiment called QUARE, an acronym for Cryogenic Underground Observatory for Rare Events, and also, appropriately, the Italian word for heart. In October of 2014, the QUARE team set a genuine world record, cooling a copper vessel with a volume of a full cubic meter, weighing somewhere in the neighborhood of 400 kilograms, down to 6 millikelvin, 6/1000ths of a degree above absolute zero. Nobody had ever cooled a mass and volume that large this close to zero before, and the cooled copper held that record temperature for more than 2 weeks straight, earning the apparatus an informal but genuinely well-supported title, the coldest cubic meter in the known universe, on the reasoning that nothing resembling those conditions is expected to occur naturally anywhere else in existence either. The whole elaborate cooling apparatus exists to serve a single, extraordinarily patient scientific goal: watching crystals of tellurium dioxide, chilled to just a few thousandths of a degree, for any sign of an exceptionally rare, still hypothetical nuclear process called neutrinoless double beta decay, a process that, if it's ever actually observed, would reshape our understanding of one of the most elusive particles in physics. And near absolute zero, matter starts doing things that look almost like special effects pulled from a science fiction film. Liquid helium, cooled far enough, becomes a superfluid, a state that flows with literally zero viscosity, zero internal friction, climbing up and over the walls of its own container in a way that looks, on video, more like a glitch in reality than ordinary physics. Some research even points toward light itself behaving in liquid-like ways under sufficiently extreme cold conditions, though that particular claim is thinner and less thoroughly documented than the core results this video is built on, so it's worth holding a little more loosely than everything else we've covered here tonight. So, can anything actually be colder than physically possible? Bring it all the way back now to the question that opened this video. Based on everything the historical record and the peer-reviewed physics actually show, across 2 centuries of careful, patient experimentation, the answer is no. Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius, has never been reached by anything, ever, in any laboratory, anywhere on Earth or in orbit, and the third law of thermodynamics, formalized by Walther Nernst back in 1906, explains in rigorous mathematical terms exactly why that will always remain true, no matter how clever the engineering gets in the decades ahead. What humans have managed to do instead is get remarkably, almost absurdly close, from Kamerlingh Onnes liquefying helium in 1908 and stumbling onto superconductivity 3 years later, through Debye and Jauch's magnetic cooling trick in the 1920s and 1930s, through Kapitsa and Landau untangling the mystery of superfluid helium in the late 1930s, through Penzias and Wilson accidentally stumbling onto the leftover heat of the Big Bang itself in the 1960s, while pointing their antenna at the same patch of sky that would later reveal a superfluid neutron star, through the dilution refrigerators and laser cooling breakthroughs of the 1960s through the 1980s, to Bose-Einstein condensates cooled below a millionth of a degree in 1995, to 500 picokelvin at MIT in 2003, to a cubic meter of copper cooled to 6/1000ths of a degree beneath an Italian mountain in 2014, all the way down to 38 picokelvin in a German drop tower in 2018, a number so small it makes the 2.7 Kelvin background hum of the universe, the coldest known naturally occurring place within it, the Boomerang Nebula, at roughly 1 Kelvin, and even the coldest failed star ever discovered beyond our solar system, at somewhere around 250 to 285 Kelvin, all look comparatively warm by an enormous margin. And what about the systems physicists describe as having negative temperature, the ones Purcell and Pound first coaxed out of a lithium fluoride crystal in 1951, and the ones Ulrich Schneider's team produced in the actual motion of potassium atoms in 2013? Those systems didn't break the floor either. They didn't get colder than impossible. What they did was find a strange, narrow staircase that only exists in systems deliberately built with an energy ceiling, a staircase that leads not downward, below zero, but upward, past the point of infinite heat, into a regime that's hotter than anything a positive temperature could ever describe. It's a loophole, but not the loophole the phrase negative temperature makes it sound like the moment you first hear it. It's not a basement below the ground floor, it's a penthouse above a roof that most buildings were never designed to have in the first place. And even that loophole, as we've spent real time seeing, isn't universally agreed upon, not even among the physicists closest to the work. Some of the very researchers working in this field argue, with serious mathematics behind them, that the whole negative temperature interpretation rests on a flawed definition of entropy, and that once you fix the definition properly, the anomaly disappears entirely, leaving nothing behind but an artifact of bad bookkeeping. Others argue just as forcefully, with equally serious mathematics of their own, that it's the proposed fix itself that's flawed, and that negative temperatures are not just possible, but genuinely inevitable in the right kind of bounded system. As of right now, based on everything gathered here, that argument is still going, quietly, in physics journals most people will never read, between scientists who respect each other's work enough to keep arguing about it in print, rather than letting it drop. So no, nothing has ever actually been colder than physically possible, and probably nothing ever will be, not because scientists haven't tried hard enough, and certainly not for lack of effort across more than a century of increasingly clever experiments. It's because the rule that forbids it was never really a limitation imposed from the outside, some arbitrary line drawn in the sand that better engineering might one day erase. It was baked directly into the very definition of what temperature means in the first place, all the way back to a young Scottish physicist working out the math in 1848. But along the way, in trying to push right up against that unreachable floor, generation after generation of physicists ended up finding something stranger than a floor being broken. They found wires that carry current forever without losing a single joule to resistance. They found helium that climbs walls as if gravity had simply stopped applying to it. They found that same strange frictionless physics playing out on its own, with no laboratory involved at all, inside the crushed core of a dead star 5,000 light-years away. They found a ceiling nobody knew was there, one that, when you push hard enough against it under exactly the right conditions, doesn't stop you cold at all. It sends you somewhere entirely unexpected instead.